interfaces part.
So
So
let's start.
let's start.
Now in
Now,
previous
in
sessions
previous
I have
sessions, I have
discussed. So
discussed. So
we
we
represent
represent
the flux of
the
atoms
flux of atoms
moving from
moving
one
from
point
one
to
point
another
to
point,
another point,
from one to
from
two,
1 to 2,
as
as
flux J
flux J
equals to
equals
minus
to
d
minus d
dou c by
dou c
dou
by
x,
dou x,
or
or
if
if
J is equal to
J is
minus
equal to
d
minus d
dc by
dc by
bx,
bx,
right? So
right?
this is
So
our
this is our
fixed first law.
fixed first law.
Then I will be
Then I will be
I'll also derive
I'll
this
also
again
derive this again.
in
So
previous
in
classes,
previous classes,
in previous
in
session,
previous session,
and I have
and I
used
have used
a normal
a normal
diagram to
diagram
represent
to
it.
represent it.
But now
But now,
I will
so I
represent
will
in a
represent in a
derive
I
it
will
in a
derive it
different
in a
way.
different way.
So
So
this
this
we started.
we
So
started.
let's
So
say
let's say
this is my
this is
material,
my material,
right?
right?
So the
So
atoms
the atoms
are moving
are
from
moving
here to
from
here.
here to
Okay.
here.
So
Okay.
this is
So
my
this is my
one plane,
one plane, one imaginary
this
plane.
is one,
This is
this is
one.
two.
This is two.
So the
So
atoms are
the
jumping
atoms are
from
jumping
one plane to
from one
second,
plane to
and
second,
also the
and
atoms
also
may
the atoms may
simultaneously jump from
simultaneously
two
jump
to
from two
one.
to
Let's
one.
say
Let's
I
say
represent
I represent
J
J
one two
one two two
as again
as
the
again
let's say it is a
the let's
random
say it is
walk.
a random
Okay,
walk.
so
Okay,
random
so
walk means the
random walk means the
property of
property
jumping
of
from,
jumping from,
let's say this is my
let's say
step
this is
one,
my step
this is
one,
my
this is
step two,
my step
this is
two,
my
this is
step
my
three.
step three.
So for example,
So,
if I
for
take
example,
my
if I
only
take
one
my only
dimensional array,
one-dimensional
so
array, so
random
the
walk
random
means
walk
the
means
probability
the
of jumping
probability of
from 1 to
jumping
2
from 1 to 2
or 1 to
or
3
one to
will
three
be
will
equals to
be equals to
probability of atoms
probability of
jumping
atoms
from
jumping from
1 to
1
2,
to 2.
right? So the
Right? So the
probability of atoms
probability of
jumping from
atoms
1 to
jumping
3
from
will
1
be
to
equals
3
to
will be
1.
equals to 1 to
This
2.
is for one
This is for
dimensional
one
array.
dimensional
Now
array.
if for
Now, if,
example
for
I have a
example,
two
if I have a
dimensional array,
two-dimensional array,
so
so
for each path
for
the
each path, the
probability will be
probability
divided
will
by
be divided
1 by
by
4
1 by
because we
4
have
because
4
we have
paths.
4 paths.
So
So
probability will be 1
probability
by
will
4.
be 1 by
Now
4.
if I take
Now,
the
if I
three
take the
dimension,
three
so
dimension,
the
so the
probability will be
probability will be
1 by
1 by
6,
6,
right?
right?
So my
So my
probability will be 1
probability
by
will be
6,
1 by 6,
right?
right?
Then
Then
the probability will
the
be
probability
1
will
by
be
6.
1 by
Now
6. Now,
what is the coordination
what is
number?
the coordination number?
Like
Like
how many
how
spots are
many
there,
spots
right?
are
For
there,
example,
right? For example, uh,
to which position
to
can
which
it
position
can
can
jump?
it can
That
jump?
will be
So that will
multiplied
be
with
multiplied with
the coordination number
the coordination number
times
times
times what, times my
times what, times my
the frequency.
the frequency,
So
right? So
let's erase the
let's
coordination
erase the
number part.
coordination number part. Okay,
Okay.
okay.
Times my
Times
frequency.
my
What is my
frequency.
frequency?
What is my
Frequency is
frequency?
my
Frequency is my
jump frequency,
jump frequency,
which will be in
which
per
will be
second.
in per second.
So what is a
So
successful?
what is a
Here
successful?
the
Here
frequency
the
is my what is the
frequency is my what
successful
is the
frequency
successful
or the
frequency
successful
or the
jump
successful
frequency.
jump frequency,
So
right?
atoms will
So
be trying
atom
to
will
jump.
be trying to
For
jump.
example,
For example,
these are the atoms.
these are the atoms.
Okay.
Okay.
Now my atom is
Now
sitting
my
here.
atom is sitting here.
Another atom. Now this
Another atom.
atom
Now
tries to
this
jump
atom
from
tries to
here
jump from
to here,
here to here,
right? So it has to
right? So it
squeeze
has to squeeze
in between this
in
atom.
between this atom.
So not every
So
jump will be
not every
successful
jump will
jump,
be successful jump,
right? So
right?
at one
So
time
at
it can
one time
try here,
it
but
can try here, but
because of the barrier
because
it
of
will
the
again come
barrier,
back.
it will again come
So
back.
that is not my
So that is
successful
not
jump.
my successful
So
jump.
here the
So here
frequency
the
is my successful
frequency
jump
is my
frequency.
successful jump
Okay.
frequency. Okay,
Times
times
n1.
n1.
What is my n1?
What is my
Number of
n1?
atoms per
Number of
unit
atoms per
area.
unit area.
So it
Okay,
is about
so it is
the
about
plane.
the plane.
So this is my plane
This is
1.
my plane
This
1.
is my
This is my
plane 2.
plane 2.
Okay, so n1 is the number
Okay,
of
so
atoms
n1 is
per
the number
unit
of
area.
atoms per
Okay,
unit
on
area.
plane 1.
Okay, on
Now
plane 1. Now,
jumping from 2 to 1.
jumping from 2
Again
to
the
1.
same
Again
1
the
by
same
6
1 by
times
6
with
times
successful
with
jump
successful
frequency
jump frequency
times
times
n2. Let's say
n2. Let's say
jump frequency is 1
jump
and
frequency is
n2.
1 and
Okay.
2. Okay,
Now
now
the net flux.
the net flux.
Suppose the moment of
Suppose
atoms
the
is from
movement of
plane 1
atoms
to
is
plane
from
2,
plane 1 to
then the
plane
net
2.
flux will
Then the
be
net
equals to
flux will be equals to
J122 minus
J122 minus
J221.
J221.
Okay.
Okay,
That is my
that is
net
my
flux,
net flux,
right?
right?
And that
Right,
is my net
that is my
flux.
net flux.
Now
Now,
upon Upon substituting this here, if you take 1 by 6 as a common, now here frequency 1 and frequency 2. Suppose if they are, suppose if I assume there are similar number of atoms on plane 1 and plane 2, okay, then this will be epsilon 1 into epsilon 2 is equal to epsilon. So times s epsilon times n1 minus n2, right? Now, what is my n1? N1 is concentration at C1 into alpha. Let's say this is my distance. I will try to draw that again. This is my plane 1, plane 2. Here between distance is delta, or I can say alpha, which is my lattice parameter. Right? Atom can jump only a single lattice parameter. It cannot jump two or three lattice parameters at a single time. Right? It needs a tremendous amount of energy to do that. Okay, so that will be C1 times alpha. Suppose if I take this as my volume, this is my area, right? Times alpha. Area times alpha, right? Number of atoms jumping from here to there. J1 to J21, right? So N1 is C1 times alpha, then N2 is C2 times alpha. Now N1 minus N2, right? So that will be C1 minus C2 times alpha. Now what is C1 minus C2? We can write it in differential form, or you can just derive it from the Taylor expansion. Okay, so that will be C1 equals to C2 plus dou C by dou X times alpha, right? Then now substituting that here, so C2 plus dou C by dou X times alpha minus C2, right? So C2 gets cancelled out, so dou C by dou X times alpha times alpha, then this will be equals to alpha square dou C by dou X. Now, if this concentration gradient is negative, then you will get a negative sign here. It depends upon how the C1 and C2 concentrations, right? If C1 is greater than C2, then this gradient will come as what? Negative. If C2 is greater than C1, then gradient will come as positive, right? This is called as downhill diffusion. This is called as uphill diffusion, as I mentioned in the previous session, right? Then the net flux will be equals to 1 by 6 alpha square times frequency times dou C upon dou X. And there is minus sign here. Right now, these terms are constant, right? The lattice parameter and jump frequency for a given temperature, right? So J net at a particular temperature will be equals to, if I write D as 1 by 6 alpha square jump frequency, then what is my D? D is my diffusivity, okay, or diffusion constant, will be equals to minus D times dou C by dou X. Now this is my fixed first law, right? So we have seen two types of primary types of diffusion mechanisms. One is my okay. Now before doing that, let's know what are our units, right? So you can write it as number of moles per unit area per unit time, right? Or you can even write kg per meter square per second. Or you can use both the units. It depends on how you are representing. Okay. Now we have two major types of diffusion mechanisms. One is substitutional Second one is substitutional, and another one is interstitial. So we have two types of major types of diffusion of atoms. One is substitutional atoms, one substitutional diffusion, one is interstitial diffusion. Now, what do you mean by substitutional diffusion? Suppose we have similar size of atoms, right? So this atom wants to try to move. Okay. So this atom wants to move. For example, this atom wants to move right from here to here. Right. There will be motion of vacancy, movement of vacancy from here to here. So let me write it like this. So this will be my atom. Now this is my atom. So this will be my vacancy. Okay. I will write it. This is vacancy. This is my atom. Okay. JV will be like this, and J atoms will be like. This is what is called as substitutional atom. Substitutional diffusion. Sorry. Now, what is my interstitial diffusion? Interstitial diffusion. Okay. What do you mean by interstitial diffusion? Now, for example, I have atoms like this. Now my interstitial diffusion, now my interstitial atom. For example, we have steel. Okay, let's talk about steel. I have carbon in iron. Okay. Now this blue atom is my carbon atom. Now these are all my black atoms are Fe atoms. Now this atom try to move in between the atoms. Okay. Now it moves from one interstitial position to another interstitial position. But here, one position to another atom position, right? So that is the main difference. Now, how do you define and what is the relation for the diffusion, right? Now we need to define diffusion relation, diffusion constant, relation for substitutional and interstitial diffusion. Okay. Right. Now, what is my term? 1/6 alpha square, that is parameter, times jump frequency. Now successful jump frequency. Now again, let's come to the energy barrier. This is my x. Now the energy will be like this. Here here the atom is at position number 1. Here the interstitial atom is in between. Here the interstitial atom is at position number 2. Right? Now how did it move? Before it was here. After a point it was on the right side. Right? It has moved from one point to another point. So this point 1, this point 2. It tries to move from one point to another point. Right? In between we have a high amount of energy because it is straining the atoms. Right? It needs energy to strain the atoms. Now this jump frequency can be denoted as, the successful jump frequency will be denoted as the mean frequency times exponential minus delta G upon kT. Now this is my successful jump frequency equation. Now this delta G can be written as sigma naught exponential. What is my delta G here? Minus delta H minus T delta S divided by kT. will be equals to the mean frequency times exponential. If I take it out, the exponential delta s by k. Now again, this can be written as a constant times this, because they are not dependent on temperature, times exponential minus delta h upon kt is the temperature term, right? Now this is the equation. Now if I try to write in that equation, the substitution, sorry, the interstitial diffusion coefficient will be written as 1 by 6 alpha square mean frequency exponential minus plus delta s upon k times exponential minus delta h upon kt. Now this whole term can be written as d naught will be equals to exponential minus delta h upon kt, right? Now from this you can obtain what is the diffusivity of any interstitial atom inside a material, right? Now this is for the interstitial atom. Now what about the substitutional atom, right? For substitutional atom, it has same relation, but only one term gets added. That is, let's write the same equation here. D equals to 1 by 6 alpha square, that is interstitial. Now this is for substitutional, okay? Sigma naught frequency times exponential delta s upon, let me write it that thing again, minus delta g upon kt. Now this is for the barrier, it must pass or it's going to squeeze the atoms, right? Now again, for substitutional atoms to move, let's say this is my substitutional atom. For my substitutional atom to move, I need a frequency here. No, sorry, not frequency, no, it's a vacancy. So for my atom to move from this point to this point, there must be a vacancy. So for any substitutional atom to move from one point to another point, it needs vacancy. Now again, how do you find a vacancy? It depends on probability. What is the probability of finding any vacancy at the next point? Will be equals to mole fraction of vacancy. Now again, what is my mole fraction of vacancy? ds equals to 1 by 6 alpha square epsilon minus delta g. This is for barrier upon kt times exponential minus delta g of vacancy upon kt. Delta g is the free energy in creation of the vacancies. Okay, so what is my xv? Xv is number of vacancy divided by total number of sites or total number of atoms. Okay, now if I write ds will be equals to di, right, di times xv, or di will be equals to ds upon xv. Now we know why the interstitial diffusion is much faster when compared to substitutional solid diffusion. Okay, now let me arrange that. So ds will be equals to 1 by 6 times epsilon naught alpha square. If I take the entropy term common, then delta s barrier plus delta s vacancy upon k times exponential minus of delta h barrier plus delta h vacancy upon kt. Right, now ds will be equals to, if I write this term as d naught, d naught of s is equals to exponential minus delta hv plus delta hv upon kt. Now this is my final relation for substitutional atom diffusion. Okay, now what is our next step? Now these are all for the ideal cases, right? So j equals to, j for interstitial will be equals to j minus di times dou c upon dou x. Right, this is for steady state. is of a steady state diffusion.
That means
That means the
the
flux or
concentration
concentration
is not
is not
a function of
a
time.
function of time.
Okay, so
Okay, so
concentration
concentration
is not
is
a
not a
function of
function of
time.
time.
Okay,
Okay,
now
now,
so
so
that means
that
concentration
means concentration
is
is
only
only
a
a function of
x
x
distance,
distance.
right? Now
Right now,
moving to the
moving
next
to
step,
the
what
next
happens
step,
if we
what
have
happens if we
unsteady
have
state?
unsteady state?
Unsteady
Unsteady
state,
state,
right? That means the
right? That
concentration
means
is
the
varying with
concentration is
time.
varying with time.
Then, for
Then,
example,
for example,
if I take
if I take the
concentration versus
concentration
x
versus x
like this,
like this,
what happens to my
what
j?
happens to my j?
J also will
J
change.
also will change.
Let's say the j
Let's say
changes
the
with
j changes with
linearly
linearly with x.
for just simplicity.
For
You
just
can
simplicity, you
take
can
any other
take
functions.
any
For
other
simplicity,
functions. For
let's just
simplicity,
take
let's just
to
take
derive a fixed
to
second
derive a
law.
fixed
Let's say
second
j
law.
is linear
Let's say
function
j
of
is
x.
linear
Let's
function
say
of
this is
x.
my j.
Let's say this is my j.
Okay.
Okay.
Now
Now,
these are the next one.
these are the next one.
This is at my
This is at my
x2.
x2.
Here I have
Here
j1.
I have
Here I have
j1.
j2.
Here I
Why?
have j2. Why?
Because j
Why?
equals to
Because j
minus
equals
v
to minus
dou
v
c
dou
upon dou
c
x,
upon
and
dou
c is
x,
not a
and
linear
c is
function.
not a
Then
linear
again,
function. Then
at
again,
1
at
we have one
one
slope.
we have
For
one
example,
slope.
at
For
1
example, at
we have.
one we have.
Let
Okay,
me
let me
erase this one.
erase this one.
Yeah.
Yeah.
So at one
So
point
at one
we
point
have slope
we have slope
like this.
like
Let's
this.
assume that it
Let's
touches.
assume that it touches.
So j
So
will have
j
one
will have
one
one
dou c by dou x.
dou c by dou x.
That is one.
That is
Now
one.
at point
Now at
x2
point x2
I have another
I
slope,
have another
right?
slope,
With a different slope.
right, with a different
Dou c
slope.
by
Now
dou
dou
x
c by dou
is
x
different.
is
So
different. So
dou c by dou
dou c by
x1
dou x1
is not
is
equals
not
to dou c
equals
by
to dou c by
dou x
dou
at 2,
x at 2,
right?
right?
Then what do we do?
Then what do we do?
Then
Then
our final flux will
our
change.
final flux will
Let's say we have
change.
j1
Let's say
minus
we have
j2.
j1 minus j2.
Now
Now,
the net
the
accumulation.
net
Now if you
accumulation.
want to know
Now,
what
if you
is the
want to know what is
accumulation
the
in
accumulation
the interval,
in the interval,
right? Because
right? Because
j1 is greater than
J1
j2.
is
You
greater
can
than
even see,
J2. You
right?
can even see,
The
right?
slopes
The
is higher at
slopes is
j1
higher at
at than
J1
j2.
at than
Then
J2.
you have
Then you have
j1 minus
J1
j2 is
minus
greater than
J2 is
0,
greater than 0,
right?
right?
But the
But
IE
the
j1
IE
is not
J1
equals
is
to
not
j2,
equals to J2,
right? Now,
right? Now,
if
if
j1 is not
J1
equals
is
to
not
j2,
equals to J2,
that means
that means,
again,
again,
for
for
example,
example,
at first I
at
have
first I have
j1.
J1.
j1 will be
J1
equals
will
to
be equals to
minus
minus
d
D
dou c
dou
upon
C upon
minus d
minus D
dou c upon
dou
dou
C
x.
upon dou x.
So at
So
point
at
1,
point 1,
dou c upon
dou
dou
C
x
upon
will
dou
give
x will
one
give
slope,
one slope,
right?
right?
So
So for
y
example, y
equals to
equals
x
to
square.
x square.
Let's just
Let's
assume
just
that the
assume the
concentration is
concentration is
changing
changing
with respect
with
to y
respect to
equals
y
to x
equals to
square,
x square,
right?
right?
So let's
So
say
let's say
this is my
this is
plot,
my plot,
this is
this
my
is my
concentration.
concentration.
Let's say
Let's say
this is my
this is my
concentration versus
concentration
x.
versus x.
Okay.
Okay.
Now,
Now,
so what is my
so
dou
what is
c
my
by dou
dou
x
c by dou
at
x
this
at
point?
this point?
Point 1
Point 1
and
and
point 2.
point 2.
So
So
let's say
let's say
at
is
1,
at 1.
this is at
This is
x
at
equals to
x
2.
equals to 2.
Now what is
Now
my
what is my
concentration
concentration
correlation?
correlation
Is
is
x square.
x square.
So dou c
So dou
upon
c upon
dou x
dou x will be
will be
equals
equals
to
to 2x,
2x,
right?
right?
Now at
Now
point
at
1
point 1
it will be
it
2.
will be 2.
What about
What
at
about
point
at
2?
point 2?
It will be
It
4,
will be 4,
right? So
right? So
the
the
slopes are
slopes are
changing.
changing. Then
Then j1
J1
minus
minus
j2
J2
is not
is
equals to
not
0.
equals to
That
0.
means
That means
either way
either way
j1 is greater
J1 is
than
greater
j2
than J2
or
or
j2 is greater
J2
than
is greater
j1,
than J1,
right?
right?
At here
At
condition
here
we just
condition, we
assume
just
that
assume
j1
that
is greater
J1
than
is greater
j2.
than J2.
Okay,
Okay,
because it is
because it is
falling.
falling. For simplicity, we are just taking
j1 and
J1
j
and
or
J
flux
or
is
flux
not
is not
flux is a linear
flux is a
function
linear
of x.
function of x.
Okay.
Okay.
Now
Now,
if
if
okay,
okay,
yeah,
yeah,
if
if
j1
J1
minus
minus
j2,
J2,
if j1
if
is greater
J1
than
is greater
j2,
than J2,
then there is a
then
net
there is a net
accumulation,
accumulation,
right?
right? For example, the flux
flowing
flowing
at 1
at 1
is greater
is
than
greater than
flux
flux
flowing at 2,
flowing at 2,
right? That
right?
means
That means
something
something
is getting
is getting
changed. The
changed,
flux
right?
is
The
getting
flux is
changed.
getting
The
changed.
flux is
The
getting
flux is
decreased
getting
from 1
decreased
to
from
2.
1 to 2.
That means the
That means the number of atoms
passing from
passing
1
from 1
is greater
is
than number
greater
of
than number
atoms
of atoms
passing from
passing
2.
from 2.
That means
That
some
means
amount of
some amount
atoms
of
are getting
atoms are getting
accumulated,
accumulated,
right?
right?
So some
So
amount of
some
atoms
amount
are
of
getting
atoms are getting
accumulated.
accumulated. That means
So the net
so the net
concentration
concentration
dou c
dou C
that's been
that's been
accumulated
accumulated
will be
will
equals
be
to
equals to
J1
J1
minus
minus
J2. It's
J2.
just
It's just
conservation of
conservation
mass,
of
right?
mass,
Some
right?
amount of
Some
is
amount of
getting
is getting
accumulated. Now
accumulated.
how
Now,
much
how much
that is
that
getting
is getting
accumulated?
accumulated?
That's what we
That's
are
what we are
deriving here.
deriving here.
So the
So
amount
the
of
amount of
concentration that's
concentration that's
being
being
getting
getting
accumulated
accumulated
will be
will
equals
be
to
equals to
J1
J1
minus
minus
J2
J2
in
in
a time
in a time
interval
interval
dt
dt
of,
of,
okay,
okay.
we
Now
do not
we
have
do
to
not
write
have to
here.
write. Yeah.
So what is
So
my
what is my
the
the
net
net
accumulation
accumulation
of
of
concentration
concentration
in an
in
area
an area
dA?
dA?
Shouldn't
I
write
shouldn't write
dA
dA
because
because
the area
the
is
area is
fixed, right?
fixed,
So
right? So
net
net
accumulation,
accumulation,
okay,
my bad.
yeah,
Yeah,
net
net
accumulation
accumulation
per unit
per
area
unit
again
area
the
again the
flux
flux
per unit
per
area.
unit area.
Okay,
Okay.
now
Now
area
area
gets
area gets
cancelled.
cancelled.
So
So
again,
again, if I use
J1 minus,
J1
how do
minus,
you
how
define?
do you
If I
define?
use the
If I
Taylor
use the Taylor
expansion, it will be
expansion, it will
easy.
be easy.
Or you can
Or you
use
can use
normal
normal
derivative
derivative
equation,
equation, which
which is
is
J1 equals
J1
to
equals to
J2
J2
dou C
dou C
upon
upon
dou X
dou X
into
into
del X,
del X,
right?
right?
So
So
this is my
this
del
is
X.
my del X.
Let me
Let
remove
me
this
remove this
equation.
equation.
Yeah.
Yeah.
J1 equals
J1
to
equals
J2
to
plus
J2
dou C
plus dou
upon
C
dou
upon
X
dou
into
X
del
into
X.
del X.
This is my
This is my
differential
differential
equation or Taylor
equation or Taylor
expansion
expansion
to
to
approximation.
approximation.
Okay.
Okay.
Now
Now, yeah.
so
So
J1 equals
J1
to
equals to
J2
J2
plus dou
plus
C
dou C
upon dou
upon
X
dou X
times
times
del X.
del X. Or
Right,
you
del
can
X,
write del
right?
X, right?
Now
Now,
here I
here
have
I have
dou C
dou C
or
or
DC
DC
will
will
be
be
equals
equals
to,
to, or you can write,
let
let me
me
write
write
it
it
dou
dou
C
C because
because we are
we are
writing it for
writing
unsteady
it
state
for unsteady
equation,
state
right?
equation, right?
So
So
C is a
C is a
function
function
of
of
both
both
time
time
and
and
temperature.
temperature.
So,
So,
not
not
temperature,
temperature,
time
time
and
and
distance,
distance.
right? So
So
that's
that's
why
why
dou
dou
C
C
will be
will be
equals
equals
to,
to
it will be dou J. I made a mistake.
yeah,
Yeah, it is dou J, not dou C, because
because
everything
everything
is
is
a
a function
function
of
of
flux,
flux,
right?
right?
So
So
that
that
was
was
dou
it's
J.
dou J.
Now
Now,
what is
what
J1
is
minus
J1
J2?
minus J2?
It
It
will
will
be
be
equals
equals
to
to
minus
minus
dou J
dou
by
J
dou
by dou
X.
X.
Again,
Again,
why
y
minus?
minus
Because
because
the
the
curvature
curvature
or
or
the slope
the
is
slope
negative,
is negative,
right?
right?
So that's
So
why I
that's
took
why I took
minus
minus
times
times
dx,
dx,
no, not
no,
dx.
not
It
dx.
should
It
be,
should be,
yeah, I can
yeah,
write it
I can
like
write
this.
it like this,
So
right? So
will be
will
upon
be
dou t.
upon dou t. Yeah,
It will
yeah,
be
it will be
dou t,
dou t,
right?
right?
Now
Now,
this will turn
this will
into
turn into
dou c
dou
upon
c
dou t
upon dou t equals to
minus
minus
or
or
dj dou j
dj dou
upon
j upon
dou x.
dou x.
Yeah, upon
Yeah,
del t
upon del t
upon area.
upon area.
Yeah,
Yeah,
dou c upon
dou
dou
c
x.
upon dou x.
The
So I
mistake
made a
here,
mistake here. I
dou
put
x
dou x
for a distance
for a
dou x.
distance dou x, right?
So
So
now
now
dou c by dou
dou
t
c by dou
equals
t
to
equals
minus
to
dou j
minus
by
dou
dou
j
x.
by dou x.
We'll
We
write
write it
dou
dou
c
c
upon dou
upon
t
dou t
minus
minus
dou j
dou j
upon
upon
dou x.
dou x.
Now what is
Now what is
flux?
flux? Again from flux,
Fix first law.
fix first law.
J equals
J
to
equals to
minus d
minus d
upon dou c
upon
by
dou c by
dou x.
dou
Right?
x,
This is my
right? This
fixed
is my
first law.
fixed first
Now
law. Now
substituting this
substituting
term
this
here,
term in here, that
it
will turn
will
out to
turn
be
out to
dou
be
c
dou c
upon dou
upon dou
t
t
will
will
be
be
equals
equals to
to
minus
minus
dou
dou
by
by
dou
dou
x
x
d
d
plus
plus
no
no
d
d
times
times
dou c
dou
upon
c upon
dou x.
dou x.
Again,
Again, parts by differential, dou c by dou t will be equals to, first I'll derive for d, then d upon dou x times dou c upon dou x plus, we have minus, right? Yeah. So minus into minus will be plus. d dou square c upon dou x square. Now, if d is not, okay, if d is not a function of x, then this term will turn out to be zero, right? Then dou c by dou t will be equals to d dou square c by dou x square. This is our fixed second law. Okay. Now, let me explain it again. There was a little miscalculation here. Let's say again, J1 is greater than J2. That means some amount of flux is being accumulated. So what is that flux? What is the amount of what is the amount that is being accumulated? That will be given in terms of concentration. So what is that concentration that being accumulated equals to how much, right? So what is our change in flux in an interval dt? Okay, so this is my total change in concentration. You can do it in this way, or this will be more straightforward to understand. Just a conservation of mass. The net accumulation will be equals to the net change in flux in an interval time dt. That's all. So dt will come here. Then it will be dou c by dou t again, and dou g by dou x. Negative curvature. So again, the whole story follows. Again, we will arrive to this point. Okay. Now, what are the terms here? C is a function of what? Distance and time. That's why we wrote it as dou c upon dou t will be equals to dou d dou square c upon dou x square. Now, if it is a steady state, suppose let's do a question. Okay. Now, if the diffusion, let's say this is my material. Okay. Now I have iron here. Let's say the classic example, the carburization. I have carbon here. Okay. This is my carbon black. Now carbon is trying to diffuse into the iron. Okay. Now let's say at point 1 and at point 2. At point 1 my concentration is C1, at point 2 my concentration is C2. Okay. Now what is the question? The first point is diffusion of carbon atoms. Okay. Now the diffusion of carbon atoms are moving in a steady state. That is my first assumption. Let me write it. Steady state. It means concentration is not a function of time. Right? Now, zero. So this term will goes to zero. Right? Concentration is only a function of x. Now, d dou square c upon dou x square will be equals to 0. D cannot be 0. So dou square c upon dou x square is 0. That means dc. Now c is only function of x, so we can remove the partial derivative and we can write the exact differential, right? So dou c upon dou x will be equals to constant c1. Again, applying differential on both, applying integration on both sides. So c will be equals to c1 x plus c2. Right? Now substituting the equation, right? For example, at x equals to 0, now boundary conditions. At x is equals to 0, C is my CS, C source. Let me write that. So Cs will be equals to
0
0
plus
plus
C2,
C2,
and
right?
because
Because
x
x
equals
equals
to
to
0.
0. Now
Now CS
Cs
will
will
be
be
equals
equals
to
to
C2.
C2.
Now we know
Now we know
the first
the first
differential.
differential.
Now
Now
C will be
C will be
equals
equals to
to C1x
C1x
plus
plus
CS.
CS.
Now
Now,
how do we
how do
find
you find
second
the second
C1?
C1?
Now we
Now,
know,
we
for
know, for
example,
example,
J.
J.
Now for
Now,
example,
for
we know
example,
what
we
is the
know what is the
concentration at
concentration
C1.
at
What
C1.
is that?
What is
Let me
that?
write
Let
it
me
again
write it again
so
so
that
that
it
it
will
will
be
be
more
more
clear.
clear.
Let's
Let's
say
say
concentration
concentration
is
is
at
at
x1,
x1,
this
this
is
is
at
at
x2.
x2.
We
We
know
know and
C1 and
C1
C2,
and C2.
and this is by
And this is by
distance.
distance.
Suppose let's say
Suppose, let's say
x.
x.
Okay, then what
Okay,
is
then
my
what is my
flux?
flux?
I know
I know my what is my diffusivity.
I
Suppose
know what is
I
the
know what is the
diffusivity of
diffusivity
atoms,
of
carbon
atoms,
atoms
carbon
in
atoms
steel.
in steel,
Particle given
at a given
temperature
temperature.
D
D
times
times
C1 minus
C1 minus
C2
C2
upon
upon
x.
x.
Right?
Right?
Now
Now,
once
once
I
I
substitute all these
substitute all these
values,
values,
I will
I
get
will get
my
my
flux.
flux.
Okay,
Okay?
JF.
JF.
I'll get my
I'll get
flux.
my flux.
Now
Now,
we know
we know
Fick's law.
Fick's law.
What is
What
Fick's
is
law?
Fick's law?
Minus D
Minus D
dou C
dou C
upon dou
upon
x.
dou x.
Right?
Right?
Now
Now,
substituting this C
substituting this C
equation there,
equation there,
that
now
J
that
will be
J will
equals
be
to
equals to
minus
minus
D
D
times
times
C1.
C1.
And what is
And
this
what
J?
is this J?
This J
This
is
J
J
is
flux,
J flux,
which we
which we
calculated there
calculated there
upon
upon
substituting all the
substituting all
C1,
the
C2 and
C1,
X
C2, and
values.
X values.
Minus D
Minus D
times
times
C1.
C1.
What is
What is
C1?
C1?
J
J
flux
flux
minus
minus
divided
divided
by
by
D.
D.
So
So
C
C will
will
be
be equals
equals
to
to
minus
minus
J
J
flux
flux
upon
upon
D
D
times
times
D
D
times
times
X
X
plus
plus
CS.
CS.
There you
There
go.
you
The
go.
whole
The whole
equation.
equation.
You can
You
write the
can write the
concentration as
concentration
a
as a
function of
function
X,
of X,
and
and you can
find
even
the
find the
flux by
flux
just
by just
substituting the
substituting the
C1
C1
concentration at
concentration at
X1 and
X1 and
concentration of
concentration of
X2
X2
divided by
divided by
the distance
the
between
distance between
those two
those
planes,
two
or
planes,
the
or
two
the two
imaginary planes,
imaginary
or
planes, or
anything
anything
that
that
you
you
are
are
imagining
imagining
where it
where
is
it
moving
is
from
moving
one
from
plane
one
on to
plane
plane
onto
two,
plane
or
two, or
the flux
the
between
flux
two
between
points.
2 points.
Okay.
Okay.
Yeah.
Yeah.
Now
Now
that is all
that is
about
all about
diffusion.
diffusion.
Okay. So
Okay.
we
So
will
we will
continue with our
continue with our
interfaces.
interfaces,
Right.
right?
Now,
Now,
what do you mean by
what do you mean by
interface?
interface?
Interface is
Interface
nothing
is
but
nothing but
a
a
boundary.
boundary,
A
a
boundary
boundary
between.
between.
A boundary
A
can be
boundary
real
can be
or
real and
imaginary, but
imaginary,
in here
but
case
in
it is
here
a
case it
real
is a
one.
real one,
So
right?
a
So a
boundary,
boundary, a real boundary
between
between
two
two
mediums.
mediums,
Right.
right?
Now,
Now,
for
for
example,
example, let's
let's say
say
solid
solid
vapor
vapor
interface.
interface.
Okay. So
Okay, so
this
this
is
is
solid
solid
vapor
solid vapor
interface.
interface,
Right.
right?
So the free
So the
energy
free
will be
energy will
equals
be
to
equals to
coming
coming
from
from
two parts.
two parts.
Let's
Let's
say
say
this
this
is
is
my
my
medium or
medium
system.
or system.
It has a
It has a
volumetric free
volumetric
energy
free
G
energy
naught.
G naught,
And another
and
thing is
another
my
thing is my
surface free
surface
energy.
free energy,
Right.
right?
So the
So
surface
the
energy
surface
will be
energy will
given
be
as
given as
surface
surface
energy
energy
times A.
times A.
Now
Now
again,
again,
this
this
is
is
not
not
my
my,
what do you call
what do you call,
the jump
the jump
frequency.
frequency.
It is my
It is
surface
my surface
energy here.
energy here.
Now
Now coming to interface, so forget about diffusion. Now let's talk about only interface here. So this term will be here surface energy per unit area, yeah, represented like this, energy per unit area. Okay, times area A naught. Right.
Again,
Again,
to know
to know
what is surface
what is
energy,
surface
surface
energy,
tension
surface
of a
tension
liquid,
of a liquid,
let's
let's
take
take
a
a
classical
classical
example
example
here.
here.
You have a
You
thin
have a
film
thin film
or a liquid
or a
film.
liquid film.
Not
I've
shown
shown
as
it's
a
a
thin
thin
film.
film.
It's
It's
a
a
liquid
liquid
film
film
formed
formed
using
using
the
the
soap
soap
bubbles,
bubbles,
where
where
you
you
can
can
easily
easily
create
create
with
with
liquid
liquid
films
films
using
using
a
a
soap
soap
bubble.
bubble,
Right.
right?
Now
Now
you have
you
your
have your
extremities.
extremities.
Now
This
this is
is
my
my
soap
soap
bubble,
bubble,
and
and
this
this
is
is
my
my
movable
movable
medium.
medium.
Okay.
Okay.
Now
Now
what I'm
what
trying to
I'm
do
trying
is
to do is
I'm
I'm
trying
trying
to
to
stretch
stretch
this
this
soap bubble.
soap bubble. right?
For example,
For
at
example, at
equilibrium,
equilibrium,
this
this
soap bubble
soap
has
bubble
some
has some
forces.
forces. Suppose
This soap bubble
this
has
soap bubble
atoms
has
here,
atoms
right?
here, right?
Now what they are
Now
trying
what
to
they are
do, they
trying to do,
attract
they attract
the stick.
the stick.
Okay, because
Okay,
atoms
because
has
atoms
a van
has
der
van
Waals
der Waals
forces.
forces,
They
right? They
attract to
attract to
potentials.
potentials.
Now,
Now,
so
so
they attract
they
here,
attract here,
right?
right?
Now let's
Now
take
let's
any
take any
imaginary line.
imaginary line here.
Okay,
Okay,
so
so
there are
there are
forces
forces
along
along
this line,
this line,
or you can say
or
the
you can say the
intermolecular
intermolecular
forces.
forces.
Here there is
Here
an
there is the
intermolecular forces,
intramolecular forces,
right? Because there
right?
are two
Because there
types
are
of
two types
things.
of things here.
Now,
Now,
this is
this is
balanced by
balanced
this
by this
force,
force,
or you
or
can
you
call it
can
as a
call it
T,
as a T,
tension,
tension,
and
and
the tension
the
per
tension
unit
per
length
unit
will be
length will be
F, which
F,
is the
which
surface
is the
tension.
surface tension.
That is
That is
maintaining it. This
maintaining
is the
it. This
force.
is the
This
force,
is the
that this is
tension
the
that is
tension
being
that is
applied,
being applied,
which maintains
which
the system
maintains the
at
system at
equilibrium. Now,
equilibrium.
what we are
Now,
trying
what
to
we
do
are
is
trying to
we
do
are
is we are
shifting away from
shifting away
equilibrium.
from
What I'm
equilibrium.
trying to
What
do
I'm
is
trying to
I'm
do is
trying to
I'm trying to
stretch
stretch
this stick
this
in
stick
this
in
direction.
this direction.
Now, this
Now,
liquid
this
film
liquid
will
film
start
will start
expanding,
expanding,
right?
right?
Just like a
Just
spring,
like a
it
spring.
tries to
It tries
oppose
to
that
oppose that
expansion,
expansion,
right? So
right?
we
So
must
we
apply
must apply
some
some
energy, or
energy, or
we must
we must
do some work
do some work
to stretch
to
this
stretch this
liquid film,
liquid film,
and
and
that work done
that work done
will be
will
given
be
as,
given as,
let's say I
let's say I
differentiate this term,
differentiate this term,
this whole
this
equation.
whole equation.
Now,
Now,
dg will be
dg will be
dg naught
dg naught
plus
plus
what's per
what's per
derivative,
derivative,
gamma
gamma
dA
dA
plus
plus
a
A
d
d
gamma,
gamma,
right?
right?
So again,
So again,
now what is the
now what is the
volumetric free
volumetric
energy?
free
So
energy?
inside the
Inside
atoms,
the atoms,
there are,
there are,
so
so
inside the
inside
system
the
the
system,
energy
the
remains
energy remains
constant,
constant,
right?
right?
The
Though
amount of
the
energy
amount
that
of
is
energy
being
that is
applied
being
on the
applied on
surface,
the surface,
right? The surface
right? The
energy is
surface
being
energy is being
changed, or the
changed,
surface
or the
area
surface area
is changed,
is changed,
right? So
right?
inside
So
the
inside
atoms
the
the
atoms,
body
the
remains
body remains
constant,
constant,
the total
the
energy,
total energy,
or you can
or
say
you can
at
say
one
at one
atom it
atom
is
it is
changing. But
changing, but
if you do the
if you do the
derivative of
derivative of
all the
all
system,
the system,
all the
all
atoms
the
inside the
atoms inside
system,
the system,
then it
then
will
it
be
will be
zero.
zero.
So that's
So
why
that's why
this will turn
this
out to
will
be
turn out
zero.
to be zero.
So
So
dou g will
dou
be
g will
equals
be
to
equals to
gamma
gamma
dA
dA
plus a
plus A
d gamma.
d gamma.
Now
Now,
differentiation with
differentiation with
respect to
respect to
the area
the area
will give
will
me
give me
surface energy
surface energy
plus
plus
a
A
change in
change
surface
in
energy
surface energy
with respect
with
to
respect to
area.
area.
Now
Now,
we have watched
we have
many
watched
times,
many
like
times,
if you
like
try
if you
to
try to
disturb a
disturb
liquid
a liquid
surface,
surface,
let's say
let's
this
say
is my
this
plane
is my
surface
plane
of
surface
liquid on
of
a lake.
liquid on a
Now
lake.
what I'm
Now,
trying to
what
do,
I'm
I
trying to do,
throw
I
a rock
throw a rock
on the
on the
surface. Now what
surface.
happens?
What happens?
It at
It
first
at
it
first
creates
it
some
creates some
disturbances, but
disturbances, but
after some
after
time
some time,
the whole
the
surface
whole
will
surface will
get
get
relaxed. So
relaxed.
what's
So
happening?
what's happening?
Whatever the
Whatever the
disturbance you try
disturbance
to
you try
create
to create
on a liquid
on a liquid
surface, the
surface, the
system will
system
try
will
to
try to
minimize that
minimize that energy
mishap.
mishap, right?
So
So
suddenly the
suddenly
energy
the energy
increases. Now
increases.
what
Now what
the
tries to
system tries to
system
do? The
tries to do?
system
The
tries to
system tries to
accommodate that
accommodate that
energy
energy
inside the system.
inside the system.
So
So if you disturb
the atoms
the
on a
atoms
liquid,
on a
they
liquid,
arrange
they
themselves
arrange
again,
themselves again,
right?
right?
So
So
in this
in this
phenomena, the
phenomena,
surface
the
energy
surface
doesn't
energy
change,
doesn't change,
right? The surface
right? The
energy
surface
remains
energy
constant
remains constant
after the
after the
disturbance, right?
disturbance, right?
In between the
In
process,
between the
it will
process, it
change.
will change.
In the process,
In
it
the
might
process, it
change,
might
but
change,
after
but
the
after
process,
the
the
process,
surface
the
energy
surface
will again
energy will
comes to the
again comes
normal
to the
value.
normal value. That means
Even on
even on
disturbing the
disturbing
area,
the area,
right?
right?
So
So
gamma
gamma
dou
do
gamma by
gamma by
dA,
dA.
dou,
So
dou gamma by
do
dou
gamma
A.
by do A.
That means
That
the
means
free
the
energy
free energy
doesn't change,
doesn't change,
right?
right?
So that's
So
what here.
that's what here.
The free energy
Free energy
of the
of
system
the system
doesn't change.
doesn't change.
That means
That means
this will be
this will
equals
be
to
equals to
zero.
zero.
So
So
dg will be
dg will
equals
be
to
equals to
the surface
the
free energy.
surface free
Now
energy.
what is my
Now, what
dg?
is my dg?
dg is my work
dg is
done.
my work done.
Work done means
Work
how
done
do you
means how do
represent
you
the
represent the
tension?
tension?
So the
So the
tension per
tension per
unit length
unit length
times
times
the area
the area
will give
will
me
give me
the surface
the
energy.
surface energy.
Right now, what is
Right
my
now, what
T
is
by
my
L?
T by L?
T by L
T
is
by
my
L is
surface
my
tension.
surface tension,
Right. So
right? So
dg
dg, you have dg upon dA, right? So this area will get cancelled. So my surface tension will be equals to surface energy. So that's why in liquids, the surface tension will be equals to surface energy. But it is not the same case for the solids, right? If you cut a surface of a solid, its surface energy gets changed, right? So that is what happening. So for liquids, and because of easy diffusion of atoms, surface energy will remain constant. But it is not true. For whom? It is not true for solids, right? So for solids, surface energy is not equals to zero. It changes with respect to the area, right? So yeah. Now then, for example, if I take a simple cubic, okay, what do you mean by simple cubic? Simple cubic is nothing but all the atoms will only occupy the corner atoms, the corner of unit cell, right? So the effective number will be one. For example, the polonium. Now, why the surface energy changes, right? Let's take that. Okay. Now let's say there is no surface area. The system is infinite, which is not ideal case, but let's just assume like that. Now, what is my delta H or LS fusion, right? That will be equals to bond energy times the number of atoms times the number of bonds per atom or the coordination number. Sorry. Right? Now, this is my LS, right? Or the fusion, enthalpy of fusion. Now, for example, now I have a surface, right? Let's say I'm talking about a simple cubic. Atoms are at corners. Now try to cut this surface along 100. Now we know, now everyone must know, or you can find this in many books. So what is 100 plane? Let's say this is my z axis, this is my x axis, this is my y axis. Okay. Now what is my 100, or you can say 010? Now the 010 will be this plane. This is my 010. Okay. Right. Now what I'm trying to do, I'm trying to cut along this surface. Okay. This surface. Okay. So this atom has lost its bond with this atom, like this one, this is two. Now first atom has lost its bond with atom two, right? Each atom is bonded to 8 different atoms, right? Coordination number is 8, right? It is surrounded by 8 atoms, right? The atom on above, the atom on left, the atom on right, atom on bottom, and atom at back. So it is bonded to all other atoms except the forward atom. So we have an energy creation times n naught times z, coordination number, times what is the atoms lost, right? No, I shouldn't write like this. Let me write it in a clear way. Now, what is my surface energy? I mean the empirical surface energy. It's not the actual surface energy. It's just the empirical surface energy. It also depends on many other parameters, right? There is a surface curvature, and and many other parameters will come into picture. So let's just write the empirical one. or the simpler one, I should say, simpler relation. So surface free energy will be equals to what is the energy per bond, right? So if I take out one atom from a crystal, what is the amount of energy it has lost? It will be given by sigma naught upon 2 divided by n naught into z, or the bond energy per atom, or you can say the energy loss per bond, right? So the total number of bonds is this one. That will be equals to our fusion, enthalpy of fusion. Now, what is per bond? That will be this, right? Now, oh sorry, I made a mistake here. Let me write it again. It won't come here. Yeah, delta H upon sigma naught by 2. This is per bond. This is for n number of bonds. This is for per bond times times what is my number of bonds lost divided by area, or area of that plane. Suppose I am talking about 0, 1, 0, area of that 0, 1, 0 plane, and here the number of bonds lost. So this is my surface energy, or the simpler relation, or a surface energy of an cut surface, or an atoms, or any surface, right? Now, coming to here, let's assume this is my x direction is my 1, 0, 0, and y direction is my 0, 1, 0. So in any direction, the number of the bonds being cut is 1, right? You can see here the number of atoms, the number of bonds being lost is only 1, because it is, let's suppose if I only focus on this area, this is my atom, right? Now, let me draw it. Suppose this is my atom, this is my main atom, okay? Now, atoms on left, atoms on right. Let's assume they are same size and same type of atoms. Okay. Now this is my focus atom. Now what about the atoms on the back? Right? These are the atoms on the back. Now, one is the atom on above, right? Above unit cell. The atom on below, the bottom one. Now, one atom is missing, right? So this atom is missing. Let me erase this part. Yeah. So let's say this is my focus atom, right? So if I see from this atom, then all the other atoms are bonded, but only this part being cut, right? Which is 0, 1, 0. Right, so this part is cut. That means there is a one bond which is broken. Right, if I cut along 0, 1, 0 surface. Now what happens if I cut along this surface? Again, this atom, this bond will be there, but this atom will get cut. So this bond will no longer be there. Right. So now, coming to this one, so the number of atoms being broken along, the number of atoms being broken, it's not a straightforward, right? Because the crystal structure is being cut at an axis, at an angle, right? It's a theta. Okay.
N
Now
will be
n will be
equals to
equals
number
to
of
number of broken
along
bonds
X
along x
plus
plus
number
number
of
of
broken
broken
bonds
bonds
along Y.
along y.
See,
See,
there
there
are
are
two
two
bonds
bonds
broken
broken
here.
here.
There
There
is
is
one
one
broken
bond
here.
broken here.
Now,
Now,
this is my
this is
lattice
my lattice
parameter
parameter
A.
A.
Let's suppose it
Let's
is simple
suppose it is
cubic.
simple cubic.
Now,
Now,
the
the
number
number
of
of
atoms
atoms
being
being
broken
broken
will
will
be
be
equals
equals
to.
to.
So
So
let's say
let's say
let's
let's
take
take
per
per
unit
unit
length.
length.
We
We
don't
don't
know
know
what
what
is
is
the
the
total
total
length,
length,
right?
right?
So
So
let's
let's
say
say
per
per
unit
unit
length.
length.
The
The
number
number
of
of bonds
bonds
being
being broken
broken
per
per
unit
unit
length.
length.
Thus,
Thus,
they
they
have
have
given
given
here
here
number
number
of
of
bonds
bonds
broken
broken
per
per
unit
unit
length
length
in
in
X
x
direction.
direction.
That
That
will
will
be
be
equals
equals
to
to
if
if
this
this
we know
we know
sines and
sines and
cosines,
cosines,
right?
right?
This is my
This
theta,
is my theta,
and
and
this is my
this
unit
is my
length.
unit length.
Then this
Then this
distance will be
distance will
equals
be
to
equals to
what?
what?
Cos
Cos
theta
theta
will
will
be
be
adjacent
adjacent
side
side
by
by
hypotenuse,
hypotenuse,
right?
right?
So this will
So
be
this will be 1
1
by
by cos theta.
cos theta.
Now what about the
Now what about
distance?
the this
This
distance?
distance
This
is
distance is
1 by
1 by
sin theta,
sin theta,
right?
right?
So this
So
distance
this
is 1 by
distance is
cos
1 by
theta,
cos theta,
and this
and
distance
this
is
distance
1 by
is
sin
1 by
theta.
sin theta.
So
Along x
this number
direction
of
plus
bonds
number of
broken
bonds
along
broken along
y direction.
y direction.
So
So
nx will be
nx
equals
will
to
be
now
equals to
again
now again.
if this is my
If this
unit
is my
length,
unit length,
let's
let's
say
say
this
this
is
is
my
my
unit
unit
length,
length, right?
and this
And
is
this is
my
my
theta,
theta.
and
Then
what
what
is
is
my
my
this
this
distance?
distance?
This
This
distance
distance
will
will
be
be
equals
equals
to
to
x.
x.
What
What
is
is
my
my
x?
x?
That's right,
That's
cos
right.
theta
Cos
equals
theta
to
equals to
adjacent side by
adjacent side by
hypotenuse. So
hypotenuse.
x
So
equals
x
to cos
equals to
theta,
cos theta,
right?
right?
So number
So
of
number of
bonds
bonds
broken
broken
along x.
along x.
So that is our
So that is
question.
our question.
How
Now,
do we
how do
arrive
we
to that?
arrive to that?
It will be
It
simple.
will be simple.
Will
Will
be
be
equals
equals
to
to
now
now
it
it
is
is
also
also
in
in
three
three
dimensions.
dimensions.
So
So
this
this
is
is
my
my
three
three
dimensions,
dimensions,
right?
right?
It
It
is
is
also
also
in
in
three
three
dimensions.
dimensions.
So
So
again
again,
taking unit
taking
length
unit
along
length
z
along
axis,
z axis also,
that will
that will
change it to
change it to
cos theta
cos theta
upon a.
upon
Now
a.
upon
Now
y
upon
upon
y
a,
upon
because
a, because
in
in
a
a
unit
unit
length
length we have
many lattice
many lattice
parameters,
parameters,
many
right?
a's.
Many a's.
So let's
So
say
let's say
10 a's
10 a's
will make
will
a 1
make a
unit
1
length,
unit length,
right? So what
right?
is
So what is
length of a?
length of
Length of a
a?
is
Length
1
of
by
a
10,
is 1 by 10,
right? So that's
right?
what
So
we did
that's
here,
what we did here.
times
Times
1 by a.
1 by a.
What
What
do
do
y
y
1 by
1
a?
by a?
Because it is in
Because
z
it is in z
direction
direction
also.
also.
So
So
sin theta by
sin
a
theta by a
into
into
1 by a.
1 by a.
Now
Now,
number of
number of
atoms
atoms
along
along
x
x
direction,
direction,
right?
right?
So that will
So
be
that will
equals
be
to
equals to
cos theta
cos theta
plus sin
plus
theta
sin theta
upon
upon
a square.
a
Now
square.
this is
Now
n
this is
total,
n total,
right? So
right?
number of
So number of
bonds
bonds
being broken
being broken
in this
in
one.
this one. Okay.
Now
Now,
what
what
is
is
my
my
surface
surface
energy?
energy?
Surface
Surface
energy
energy
will
will
be
be
given
given
by
by
bond
bond
energy
energy
of
of an
an
each
each bond
bond
times
times
the number of
the number
bonds,
of bonds,
right?
right?
This
This
will
will
be
be
equals
equals
to
to
cos
cos
theta
theta
plus
plus
sin theta
sin theta
upon
upon
a square.
a square.
So
So
surface energy
surface
will be
energy will
equals
be
to
equals to
bond length
bond
upon
length
2
upon 2
times a
times
square
a square
cos theta
cos theta
plus
plus
sin theta.
sin theta.
Now
Now,
I
I
will
will
write
write
that
that
equation
equation
again.
again.
So
So
sigma
sigma
naught
naught
upon
upon
2
2
a
a
square
square
times
times
cos
cos
theta
theta
plus sin
plus
theta.
sin theta.
If I take
If I
theta
take
values
theta values
positive value.
positive value. Okay.
Now,
Now,
if I try
if
to
I
draw
try to draw
on a polar
on a polar
axis,
axis, right?
so my
So
radius
my
will be
radius will be
what?
what?
Surface energy,
Surface energy,
and my
and
x
my
is
x is
theta
theta
for the
for
polar
the
axis.
polar axis.
Okay.
Okay.
So how
So
does it
how
look
does
like?
it look like?
So for
So
first
for first
quadrant,
quadrant,
it will
it will
look like
look
this.
like this.
Okay.
Okay.
Now for the
Now for the
second
second
quadrant,
quadrant,
it
it
will
will
look
look
like
like
this.
this.
Now
Now
for
for
the
the
third
third
quadrant,
quadrant,
it
it
will
will
look
look
like
like
this.
this.
And now for
And
the
now for
fourth
the fourth
quadrant,
quadrant,
it will look
it will
like
look like that,
right.
right?
Now what is
Now
my
what is
surface
my surface
energy?
energy?
The energy
The
value
energy
will be
value will be my
the
the
projection vector.
projection vector.
The
vector from
origin
origin
to the
to the
surface,
surface,
right?
right?
Or
Or
if you try
if
to
you try
draw
to draw
a
a
tangent,
tangent,
so the
so
point
the
where the
point where the
tangent touches
tangent
the
touches
curve,
the curve,
that will be my
that will be
surface
my
energy.
surface energy.
It
It
will
will
be
be my
gamma
gamma
for an
for
angle
an angle
theta.
theta.
See,
See,
we can
we
see
can see
two terms
two
here.
terms here.
One is the
One is the
maximum point,
maximum point,
another
another
is
is my
minimum point.
minimum
How many
point. How
minimum
many
points I
minimum
have?
points I
One,
have? One,
two,
two,
three,
three,
four.
four.
Right?
Right?
If I try
If
to
you try to
draw tangent
draw
at that
tangent at
point,
that point,
it will look
it will
like
look
this.
like this.
At two,
At
it
two,
will look
it
like
will
this.
look like
At
this. At
three,
three,
at four.
at four.
So
So
whenever
whenever
the system
a system
tries to
tries
maintain
to
an
maintain an
equilibrium
equilibrium
or tries to
or
have an
tries to have an
equilibrium, it
equilibrium,
tries
it
to
tries to
maintain a
maintain
minimum
a
surface
minimum
energy
surface energy
or a minimum
or
energy
minimum
of the
energy
total
of the
system.
total system.
And that
And of
energy
that
may be
energy may
minimum
be
for the
minimum for the
volumetric
volumetric
free
free
energy
energy
and surface
and
free
surface
energy
free
and every
energy
free
and every
energy
free energy
that we are
that
linked
we are
with.
linked with.
Okay, so the
Okay,
system
so the
tries to
system tries
maintain
to
the minimum
maintain the
free
minimum
energy.
free energy.
Right, the minimum
Right,
free
the
energy is
minimum free
obtained
energy
on
is obtained
these
on
four
these
surfaces.
four surfaces.
So the
So the
equilibrium
equilibrium
shape
shape
of this system
of the
is
system is
the square.
the square,
Right?
right?
So
So
this is called as
this is
Wolff
called as Wolff
construction.
construction.
Suppose
Suppose
equilibrium shape,
equilibrium shape,
any
any
equilibrium shape,
equilibrium shape,
right?
right?
Any
Any
equilibrium shape
equilibrium shape
tries to
tries to
maintain
maintain
equilibrium
equilibrium
tries
or
to
tries
obtain
to obtain
any equilibrium.
any
I should
equilibrium,
write
I
any
should write
equilibrium
any
system
equilibrium
here
system here
like
like
this.
this.
Any
Any
equilibrium
equilibrium
system
system tries to maintain
obtain an
obtain an
equilibrium shape,
equilibrium shape,
then it
then
must
it must
satisfy
satisfy
this
this
equation:
equation:
sigma
sigma
I
I sigma I ai
equals
will
to
equals to
minimum,
minimum,
not zero.
not zero.
It is for
It is for
minimum.
minimum.
If it is zero,
If
it
it
is
is
an
zero, it is an
like
like
we can call it
we
as an
can call it an
infinite,
infinite, uh,
which doesn't have
which
any
doesn't have
area.
any area.
It's just an
It's just
infinite
an
system,
infinite system,
which has no
which has
ends,
no ends,
which is not
which is
possible.
not possible,
Right.
right?
So
So
this is my
this is my
condition
condition
for this
for
type of
this
earth
type of earth
construction.
construction. Okay.
Now
Now
that is about
that is
solid
about solid
vapor
vapor
interface.
interface. Now
Now
what
what about
about
solid-solid
solid solid
interface?
interface?
Okay, or we
Okay,
can
or
call
we
it
can
as
call it as
interface.
interface,
Solid-solid
solid solid
interface.
interface. Okay.
Okay. Now we can have
Now
two
we can have
types,
two
right?
types,
If we
right?
have
If
same
you have
phases,
same phases,
both sides.
both sides.
Let's say
Let's say
this is my
this is my
boundary. Here I
boundary.
have
Here I
phase
have
one.
phase
Here I
one.
also
Here
have
also
phase
I
one.
have phase one.
Okay.
Okay.
So
So
it cannot be
it
this
cannot be this
straightforward,
straightforward,
right?
right?
So
So
we can
we
have
can have
two types.
two
One
types.
is the
One is the
rotation one.
rotation one.
You can
You can
as
as
a
a
tilt boundary.
tilt boundary.
This can be
This can be
represented as
represented as a
tilt boundary.
tilt
And
boundary,
this one
and
as
this one as
twist
twist
boundary.
boundary,
Right. So
right?
this
So this
boundary
boundary
will be
will be
at an
at
angle
an
with
angle
respect
with
to
respect
P1
to
and
P1 and P1
with respect to
with
two
respect to two
phases.
phases,
Right.
right?
Suppose if I have
Suppose if I
pure
have
copper.
pure copper, right?
So there are
So
two
there are
grains
two
of
grains
copper.
of copper.
This is
This
grain
is
one.
grain one.
This is
This is
grain
grain
two.
two.
Now they are
Now they are
aligning at a
aligning at
particular
a particular
angle.
angle,
Right. The
right? The
orientation is
orientation is
different
different
in grain one
in
and
grain
grain
one
two.
and grain
That's why
two.
we
That's
call
why
it
we
as two
call as
different
two
grains.
different grains.
The major
The
difference
major
between
difference
them
in
is their
between them is their
orientation,
orientation,
or, of the atomic
of the atomic
planes.
lengths,
Right.
right?
Now
Now
that's about
that's about
P1 and
P1
G1
and
and G2.
G1
Now
and
what
G2.
is my
Now what
tilt
is my
boundary?
tilt
Tilt
boundary?
boundary is
Tilt
nothing
boundary is
but
nothing but,
let's
let's
suppose
suppose this is my
grain one
grain one
and this is
and
my,
this is my,
let's say,
let's say,
grain two.
grain two.
Now what I'm
Now
trying
what
to
I'm
do
trying
is
to do
I'm
is
trying to
I'm
tilt
trying to
it,
tilt it,
right?
right?
Tilting with
Tilting with
respect to
respect to
this guy.
this guy.
Let's say this
Let's say
has a
this has a
surface area.
surface area.
This grain,
This grain
this is the
is
grain
the
one
grain one
surface,
surface,
right?
right? this grain one surface.
Now
Now
let
let
me
me
draw
draw
grain to
grain to
surface.
surface.
Now what I'm
Now
trying
what
to
I'm
do
trying
is
to do
I'm
is
trying to
I'm
tilt
trying
it.
to tilt it.
Tilting
Tilting
is
is
nothing
nothing
but
but
suppose
suppose
this
this
is
is
my
my
surface.
surface.
It will
It will
move at a
move
different
at a
angle.
different angle.
Let's say
Let's say
this is my
this is my
surface
surface
of grain.
of grain 2.
So we
So
have
we have
a tilting,
a tilting,
right? Movement
right?
of
Movement
atomic
of
planes
atomic
from
planes
if
from,
I
if
see
I
from
see
top
from top
projection,
projection,
it will look
it
like
will
this.
look like this.
There is an
There is
angle
an angle
theta.
theta
That is
that
tilting.
is tilting.
Now,
Now,
how it is
how it
tilting?
is tilting?
Is it
Is it
parallel or
parallel or
perpendicular?
perpendicular?
Right?
Right?
Now,
Now,
my plane
my
is this
plane
one.
is this one.
This is my
This
plane.
is my plane.
Right?
Right?
Now,
Now,
it is
it is
moving parallel
moving
to that
parallel
plane.
to that plane.
Right?
Right?
This is
So
my
this is my
plane.
plane.
I'm
I'm
rotating
rotating
with respect
with
to
respect to
this.
this. Right?
This line is
This line
parallel
is
to that.
parallel to that plane.
Now,
Now,
what about the
what about
twist?
the twist?
Right? As you
Right?
can
As
see
you can
here.
see here.
So
So
this is my
this is my
plane.
plane.
What I'm trying
What
to
I'm
do is
trying to do is
I'm trying
I'm
to
trying to
rotate.
rotate.
I'm
That's
just
I'm just
separating two
separating two
surfaces
surfaces
for
for
understanding.
understanding.
Okay,
Okay,
so
so
this
this
is
is
my
my
G1,
G1,
this
this
is
is
my
my
G2.
G2.
Now what I'm
And
trying
what
to
I'm
do
trying
is
to do is
I'm trying to
I'm
put
trying to
this guy
put this guy
stationary and I'm
stationary
trying
and
to
I'm trying to
rotate this one.
rotate this one.
Right?
Right?
So
So
yeah,
yeah,
this
this
surface,
surface,
this
this
A1,
A1,
A2.
A2.
So
So
A1 is
A1 is
rotating with
rotating with
respect to
respect to
A2,
A2,
right?
right?
In a
In
particular
a
angle
particular
or
angle or
particular
particular
clockwise or
clockwise or
anti-clockwise.
anti-clockwise.
So that
So
is
that
my
is my
twist boundary.
twist boundary.
Now,
Now,
during this
during this
tilting boundary,
tilting, or
there are different
there are
types of
different
tilt
types of tilt
boundaries.
boundaries.
So first,
So
let's talk
first, let's
about
talk about
low angle
low angle
tilt
tilt
boundaries.
boundaries.
Low angle
Low
tilt.
angle tilt.
Okay.
Okay,
Low
so
angle
low angle
tilt
tilt
boundaries.
boundaries.
That
That
means
means
the
the
angle
angle
is
is
below
below
15%, 15 degrees.
15 degrees.
Now,
Now,
how does that
how
look
does
like?
that look like?
So
So
this is
this is these are my two set of lines of same species,
G1,
G1,
G2.
G2.
Now it
Now
is
it is
tilted with
tilted
respect
with
to
respect to
this line.
this line.
Right now, how
Right
do
now,
we
how do we
accommodate
accommodate
these gaps?
these
Right.
gaps? Right.
These are
So
just
these are
fault
just
areas.
fault
Now, how do we
areas. Now, how do we
accommodate those fault
accommodate those
areas?
fault areas?
By
By
introducing
introducing
the edge
the edge
dislocation.
dislocation.
That's why
That's why
if
if
we
we
locate
locate
any low
any
angle
low
tilt
angle tilt
boundary,
boundary,
low
low
angle
angle
tilt
tilt
boundary,
boundary,
we can
we
see.
can see.
So
Okay,
if we
so
try
if
to
we try
locate
to locate
any low
any
angle
low
tilt
angle
boundary,
tilt boundary,
we
we
can
can
see
see
an
an
array
array
of
of
dislocations.
dislocations.
Array
Array
of
of
edge
edge
dislocations.
dislocations.
What about
What about
the low
the
angle
low
twist
angle twist
boundary?
boundary?
Low
Low
angle
angle
twist
twist
boundary.
boundary.
You will
You will
find a
find
cross
a
grid
cross
of
grid of
edge
edge
dislocations, screw
dislocations, screw
dislocations.
dislocations. So that is a major difference. So we cannot just see and tell, oh, like this is
Screw
screw
dislocation. It is quite
dislocation. It is
complex.
quite
You have
complex. You
to
have to
picture in your
picture in
mind
your
how the
mind
screw
how the screw
dislocation looks.
dislocation
It's
looks.
just
It's
like a
just
screw,
like a screw,
right?
right?
So
So
that's all.
that's
Now
all.
that is the
Now that is the
traveling of our
traveling of
budget
our
vector.
budget
So
vector.
that's why
So that's why
the name
the
came
name
the screw
came the screw
dislocation.
dislocation.
That is my
That is my
traveling of
traveling
a
of a
budget vector
budget
along the
vector
budget
along the
circuit.
budget circuit,
Right?
right?
Now,
Now,
what is
now what
happening
is
here?
happening here?
Now, in low
Now
angle,
in low
suppose
angle, suppose
if I
if
have
I have
two
two
grains
grains
that are
that are
perfectly matched,
perfectly matched,
right? There is
right?
no
There is
surface
no
energy
surface energy
created.
created.
So this
So
can be
this
taken
can be
as a
taken
single
as a
system,
single system,
single grain,
single grain.
simple, right?
Simple, right?
Now,
Now, what happens
if
if
I
I
try
try
to
to
twist
twist
the grain
the
boundaries,
grain boundaries? Two grain boundaries.
this
Is
is
my
my
G1 is
G
G
to
to
tilt.
tilt.
Now,
Now,
upon
upon
tilting,
tilting
with respect
with
to an
respect to
angle
an
theta,
angle theta,
right?
right? We are
A surface
creating a
energy,
surface energy,
extra surface
extra
energy,
surface energy,
right?
right?
Now, what
Now,
happens to
what
the
happens to
surface
the
energy?
surface energy?
Whether it
Whether
increases
it
or
increases or
decreases?
decreases?
Obviously,
Obviously,
it
it
will
will
increase
increase
because
because
here
here
you
you
have
have
no
no
surface
surface
energy,
energy,
but
but
here
here
we
you
have
have
a
a
surface
surface
energy
energy
that's
that's
being
being
created,
created,
right? So there
right?
is an
So there is
increase
an
in
increase
surface
in
energy.
surface energy.
Now,
Now,
how does the
how does
surface
the
energy
surface energy
goes
goes
on
on
increasing
increasing
with
with
theta,
theta,
right?
right? So, for example, let's say let's draw here. This is my surface energy of the tilt boundary, and this is the tilting angle. At first,
zero,
0
because
because
there
there
is
is
no
no
surface being
surface
created,
being created,
so no
so
surface
no
energy.
surface energy.
It goes on
It goes on
increasing,
increasing,
and
and
it
it
will
will
flatten
flatten
out,
out,
right?
right?
So
So
this is
this
10
is
to
10
15
to 15
degrees.
degrees.
Now, why
Now,
it is
why
getting
it is getting
constant?
constant?
Because
Because
upon
upon
tilting,
tilting,
more
more number of
dislocations are being
dislocations are
added,
being added,
right? The number
right?
of
The number of
dislocations are
dislocations are
increased
increased
while
while
increasing
increasing
the tilt
the tilt
angle,
angle,
right? The number
right?
of
The number of
dislocations
dislocations
gets increased
gets
while
increased while
increasing the tilt
increasing the
angle.
tilt
So the
angle.
more
So the
number
more
of
number of
dislocations come
dislocations
close
come
together,
close together.
at one
At
point,
one point,
these
these
dislocation
dislocation
fields
fields with
overlap, and
overlap,
they
and they
sometimes
sometimes they
cancel
cancel
out,
out,
sometimes
sometimes they
they mix.
mix.
So
So
that's what
that's
happening.
what
So the
happening. So
surface
the
energy
surface
will
energy
remain
will remain
constant
constant
after
after
attend to
a 10
15
to
degrees,
15
right?
degrees.
So
So,
these
and these
are called
are
as
called as
random high
random
angle
high
grain
angle grain
boundaries.
boundaries.
Random high
Random high
angle
angle
grain
grain
boundaries.
boundaries.
Now,
Now,
there is
there
a
is a
special
special
case
case
where even
where
if you
even if you
increase the angle
increase the
tilt
angle
angle
tilt
from 10
angle
to
from 10
15
to 15
degrees,
degrees,
at one
at one
particular
particular
angle,
angle,
the
the
atoms,
atoms
you can see
you can
here,
see here,
at one
at one
particular
particular
angle
angle
or one
or one
particular angle,
particular angle,
you have
you
a
have
plane,
a plane
or you have
or
a
you have a
boundary
boundary
on which,
on which
on either
on either
sides, the
sides
atoms are
the
on
atoms are
mirror
on
images.
mirror
You
images,
can see
right? You can
if you
see
can keep a
if you
mirror
can keep
here,
a mirror
it will
here, it
exactly
will
look like
exactly
mirror
look like
image
a
of
mirror image of
one side.
one
For
side.
example, if
For
I see
example,
it
if I
from
see
here,
it from here,
the one will be
the
mirror
one will be
image of
mirror
2,
image of a 2,
two will be
or
mirror
2 will
image
be
of 1,
mirror image of 1,
and this
and this
boundary is called
boundary
as
is called as
twin boundary,
twin boundary,
right?
right?
Now here,
Now here
the surface
the
energy
surface
is
energy
minimum,
is minimum,
right? Surface
right? Or
energy is
surface
low.
energy is low. I shouldn't say
It
minimum.
is a low
It is a low
at a
at a
certain
certain
tilt angle.
tilt
So tilt
angles,
angle,
tilt angle,
right?
right?
So this
So this
twin plane
twin
is
plane is
extremely
extremely
sensitive to the
sensitive to the
angle of
angle
rotation,
of rotation,
a tilt
a
angle,
tilt angle,
right? So
right?
you can
So
see
you
here,
can see
this
here,
is my
this is my
gamma, this is
gamma,
my
this is
theta.
my theta.
So at
So at
certain position
certain
theta
position,
is equal
theta
to
is
theta
equal to
naught,
theta naught.
the surface
The
energy is
surface energy
minimum.
is minimum.
But
But
even if I
even
try
if
to
I
move
try to move
slightly,
slightly,
theta
right,
naught
theta
plus
naught plus
delta theta,
delta theta,
the,
the,
the surface
the
energy
surface
shoots up,
energy shoots up,
right?
right?
So that's why
So
the
that's why
twin
the twin
boundary or
boundary or
twin boundary
twin
surface
boundary
energy
surface energy
is
is
extremely
extremely
sensitive to the
sensitive to
tilt
the
angle,
tilt angle,
right?
right?
Now,
Now,
there are
now
different
there are
types of
different types of
the different
the different
conditions
conditions for
to have a
to
minimum
have a
amount of
minimum
surface
amount of
energy
surface energy
in high
in
angle
high angle
grain
grain
boundaries.
boundaries.
Okay,
Okay,
so
so
the sir has
sir has
mentioned in his
mentioned in his
lectures
lectures
there
in
are
there as
KS,
KS,
LW, different
LW,
types of
different types of
conditions
conditions
for,
for,
right,
right,
to have
to have
minimum surface
minimum
energy
surface
or to
energy or
have
to have
equilibrium
equilibrium
grain
grain
boundary
boundary
shape,
shape,
right? And there
right?
is
And
another
there is
point.
another point.
For
For
example,
example,
if
if two grain
two
boundaries, if
grains
two
meet,
grains meet,
right, they
right,
meet
they meet
at a
at
plane.
a plane.
Now what
Now,
happens
what
if three
happens if three
boundaries meet?
boundaries meet?
Three grain
Three
boundaries
grain
are
boundaries are
meeting.
meeting.
Those three
Those
grain
three
boundaries
grain
are
boundaries are
meeting along
meeting
a line.
along a line.
And what about
And
the
what
four
about the
grain
four
boundaries?
grain
The four
boundaries? The
grain
four
boundaries
grain
will be
boundaries will
meeting
be
at
meeting
a
at a
point.
point.
So
So
that is all
that is
about
all
the same
about the
type of
same type of uh,
grains. Now what
grains. Now,
happens
what happens
if there are
if there are
different
different
phase,
phase,
right? So
right? So
that's where
that's where
we come
we
at
come at the
interface
interface
interfaces,
interfaces,
right?
right?
So
So
interface
interface two different phases. Right? Let me add this here. So suppose if I have an alpha and if I have beta, alpha has different crystal structure, crystal structure than beta. Right? That means let's say alpha is my FCC and beta is my BCC. Or let's say my alpha is FCC and beta is also FCC, but the chemical species are different, right? So the chemical species are different. That means their lattice parameter is also different. Lattice parameter is different. So that's why we call it as a is an interface between two different phases or interfaces, right? Now, how many types of mechanism we can follow? So first one is coherent interface. What do you mean coherent interface? On either side. Let's suppose this is my boundary between these two phases, alpha and beta. Let's assume this is as alpha and the down one is as beta. Right. Now there are two phases. It has a boundary B. Okay. So this is my boundary B. Right. And these are A atoms. The black atoms are A atoms and white atoms are B atoms. Now, what do you mean coherent interface? The atomic arrangements on both sides are almost equal, or the atomic configuration across the boundary is same. Then we call it as a coherent interface. Now, this coherent interface cannot be this much straightforward, where the atoms are like exactly same or the mirror image on both sides. They can be rotated to certain angle, right? But still, they might have the same configuration. Like here, right? This is my grain one. This is my grain two. Grain two has atomic planes. Let's suppose this is my 100 and also this is my 100. So 100 of G1 is at an angle with G2, right? But still, across the boundary, they have same atomic configuration. We can even have this type of structure. And in some cases, in some cases, we can see even though the second phase has a slightly different lattice parameter, the atomic planes try to shear or try to here the atomic planes are either getting stretched, right? Here the atomic planes are trying to stretch, and these atomic planes are trying to compress this one, right? So the forces are balanced, but still the whole atomic planes are being stretched. They are not in equilibrium condition, even though the atomic configuration on both sides of the boundary is same, but to accommodate this kind of structure, there should be some amount of energy that must be supplied, right? Because the system is getting strained, or the atomic planes on both sides are getting strained. One is getting elongated and another one is getting compressed, right? So here the extra energy is getting added, the strain energy or volumetric strain energy is being added, but the surface energy is getting minimized, right? So here we can see, what do we see? We see the coherency strains, right? The straining of atomic planes in both phases to accommodate the minimum surface energy. right?
So
So
even though
even though
we
even
have
though we have
minimum
minimum
surface
surface
energy,
energy,
we have
we have
we still
we
have
still have
chemical free
chemical
energy,
free energy,
right? Why?
right? Why?
Because
Because
the
the
atoms
atoms
of
of
A
A
are
are
bonded with
bonded with
B.
B.
So there is
So there
change
is
in
change
chemical
in
free
chemical
energy,
free energy,
right? So
right?
that is
So that
given
is
by
given by
gamma
gamma
CH,
CH,
because A is
because
not
A is not
bonded with A
bonded with
atom,
A atom,
so it
right?
is
So it
bonded
is
with B.
bonded with B.
So there is
So
a
there is a
change
change
in chemical
in
free
chemical
energy.
free energy.
So there are
So
two
there are
types
two
of
types of
surface free
surface
energies.
free energies.
One
One
is because
is
of
because of
creation of a
creation of a
surface.
surface.
Two
Two
is because
is
of
because of
one
one
is
is
because
because
of
of
broken bonds.
broken bonds.
One is
One
because
is
of
because of
different chemical
different chemical
species,
species
chemical
or
surface
chemical
free
surface
energy,
free energy,
right?
right?
So
So calculate
here
it
itself,
here itself.
gamma total
Gamma
will be
total will
equals
be
to
equals to
gamma
gamma
surface free
surface
energy
free energy
plus
plus
gamma
gamma
chemical free
chemical
energy,
free energy,
right?
right?
Now
Now
this is our
this is our
coherent
coherent
interface.
interface.
Now the
Now
second
the
one is
second one is
semi-coherent
semi-coherent.
semi-coherent
Semi-coherent
interface.
interface.
At name
At
itself
name itself
suggests
suggests
some parts
some
are
parts are
coherent,
coherent,
some parts
some parts
are
are
incoherent,
incoherent,
right?
right?
So you can
So
see
you can
here
see
the atomic
here the
planes are
atomic
being
planes are
matched,
being matched.
but here
But here
the bonds are
the bonds
broken.
are broken.
Here the
Here
atomic
the
planes are
atomic planes
matched.
are
Here
matched. Here one
atom
one
plane is
atom
missing.
plane is missing.
Here
Here
the atomic
the
planes
atomic planes
are matching.
are matching.
That's why we call
That's
it
why we
as
call it as a
semi-coherent
semi-coherent
interface.
interface.
Now this
Now this
strain,
strain,
for
for
example,
example,
here
here
incoherency strain.
incoherency
Here you
strain.
can
Here
see
you can see
there is a
there is a
coherency strain.
coherency
Now
strain.
what
Now
happens if
what
I try
happens if
to
I try to
increase
increase
the lattice
the
parameter
lattice
of beta,
parameter of beta,
right?
right?
If I try
If
to
I try to
accommodate
accommodate
a different
a
lattice
different lattice
parameter,
parameter,
more
more
larger lattice
larger
parameter
lattice
when
parameter
compared
when
to
compared
alpha,
to alpha,
or
or
lesser or
lesser
larger
or
lattice
larger
parameter,
lattice
a totally
parameter, a
different
totally different
parameter,
parameter,
then
then
some parts
some
of
parts of
atomic planes will
atomic
get
planes will
matched,
get
and
matched, and
whatever
whatever
the atomic
the
planes that
atomic
are
planes
being
that are
left
being
over
left over
will be
will be
accommodated
accommodated
by
by
an
an
edge
edge
dislocation.
dislocation.
Now this edge
Now this edge
dislocation
dislocation
will
will
decrease
decrease
will decrease
will
the total
decrease the
surface
total
free
surface
energy,
free energy,
right?
right?
So
So
in
in
semi-coherent
semi-coherent
interfaces,
interfaces,
there is an
there is an
introduction of
introduction of
introduction of
introduction of
dislocations
dislocations
to
to
minimize
minimize
surface free
surface
energy,
free energy,
right?
right?
Now,
Now,
how do you find
how
the
do you
distance
find the
between the
distance
two
between the
dislocations,
two edge dislocations,
right?
right?
It's again
It's
using the
again
unit
using the
length
unit length
one.
one.
Okay,
Okay,
so the number
so
of
the number
arrays
of arrays
or the
or
number of
the number of
atomic planes
atomic planes
in
in
alpha phase.
alpha phase.
Let's say this is
Let's say this is
alpha and this
alpha
is
and
beta.
this is beta.
What is my
What is my
uh,
uh,
no? For
no? For
semi-coherent
semi-coherent
interfaces,
interfaces,
we
we
introduce a
introduce a
parameter,
parameter,
right?
right?
And that is
And that
parameter is
is
a
parameter
misfit
is a misfit
parameter,
parameter,
right? So
right? So
this
this
misfit parameter
misfit
can be
parameter can be
represented
represented
as
as
d
d
or
or
interatomic plane
interatomic plane
spacing
spacing
between d
between
beta
d beta
minus
minus
d
d
alpha
alpha
upon
upon
d
d
alpha.
alpha.
This is my
This
misfit
is my misfit
parameters.
parameter.
Okay.
Okay.
Now
Now the number of dislocations, sorry, the
the
number
number
of
of
atomic
in
planes
alpha
in alpha
phase
phase
will be
will
given
be
as
given as
per unit
per
length.
unit length. The number of atomic planes
In
in
alpha
alpha per unit length
will
will
be
be
given
given
as
as
1 by
1 by,
right.
right?
So
So
1 by
1 by
d
d
alpha,
alpha,
number of
number
atomic
of
planes in
atomic planes
alpha.
in alpha.
Again,
Again,
the number of
the number
atomic
of
planes
atomic
in
planes
beta
in
will be
beta
given
will be
by
given by,
per unit
per
length
unit length will be given
1 by
by
d
1 by
beta.
d beta.
Now,
Now,
the number
the
of
number of
atomic planes
atomic planes
that are not
that are
being
not
covered,
being covered,
the
the
number
number
of
of
atomic
atomic
planes
planes per unit that
that
are
are not
not
being
being
covered,
covered.
that means
That means
the number of
the
atomic
number of
planes
atomic
that are
planes that
left
are
over,
left
right?
over, right?
Just like here,
Just like here,
will be equals
will be
to
equals to
1 by
1 by
d
d
alpha
alpha
minus 1
minus
by
1 by
d beta.
d beta.
Now,
Now,
that
that will give rise
n
to
number of
n number of
dislocations.
dislocations.
Now,
Now,
what is the
what is
distance
the distance
between
between
one
one
dislocation?
dislocation?
This is for
This
n
is
number
for
of
n number of
dislocations. Now, what is
dislocation.
the
Now,
distance
what is the
between
distance? One
one
dislocation.
dislocation? That will be
That
equals
will
to
be equals
1
to
by
1 by 1 by 1 by d alpha minus 1 by d beta. Now, this d, the distance between two dislocations, will be equals to 1 by d beta minus d alpha, right, divided by d alpha d beta. And this will be equals to d d alpha d beta upon d alpha minus d beta. You can neglect the negative sign. So d will be equals to d beta upon misfit parameter. Now again, if d alpha is approximately equals to d beta and also d beta, that means d beta will be d alpha. Oh, wait a minute. So d alpha plus d beta by 2, right? Then our Berger vector will be d beta, right? This will be equals to Berger vector. Right? Then the distance between two dislocations will be equals to Berger vector divided by a misfit parameter. So that's how we arrive to this equation. Right. Now, if my lattice parameter is again increased from semi-coherent interface value to a greater value, then we will have incoherent interfaces. Right, just like here. Oh, yeah, where the atomic matching is completely different. Right, so this is the incoherent interfaces. Now, incoherent interfaces have large amount of surface free energy values, right? So again, if I gamma and the lattice parameter difference, right? Or misfield parameter, you can take any of those. Then it will increase, and then again it will maintain a constant value. Why? Because why? Because same the dislocations distance in between will decrease, right? That means the d will go down, so which will result in overlapping of dislocation fields, right? So that's why it will reach a constant value or flatten out. Now, that is all about different interfaces and the surface energies of different types of phases lattice parameter, right? We can have seen this coherent, semi-coherent, and incoherent interfaces, right? Now moving on to the surface energy of the specific atomic planes, right? Let me add few more slides. Yeah. Let's say the surface energy of FCC atomic planes. Right? Now, what do you mean by surface energy? Again, the surface energy is given as bond energy per unit length, which is 2 times Z times N naught. This will be my constant times area of that plane by the number of atoms lost. Right. So let's do it for 1, 1, 1, 1 0 0 1 1 0.
Okay.
Okay.
Next
Next
one
one
is
is
2
2
0 0
0 0
and
and
2
2 2
0.
0.
Right.
Right.
I'm going to do
I'm
1
going to
1
do
1
1 1
1
1
1
1
1
1
0
1
0
0
1
0
1 0
1 1
2 0
0 2
0.
0 0.
You can
You can
do it for
do it for
2 to 0.
2 to 0.
If
If
you do not
you do not
come to that
come to
solution,
that solution,
you
you
can
can
just
just
mail me.
mail me.
I can share
I
that
can share
solution
that
for
solution.
you.
Okay.
Now
Now
let's draw
let's draw
simple cubic
simple
units.
cubic unit itself.
Right.
Right.
So
So let's
let's
draw
draw
the
the FCC.
FCC. This
This
is
is my
my
FCC.
FCC.
Right.
Right.
Now
Now
let
let
me
me
draw
draw
my
my
atoms.
atoms.
Right.
Right.
So
So
my
my
atoms
atoms are
are
these are my corner atoms. These are my corner atoms, right?
now
Now
the
the
surface
surface
atoms
atoms
we draw
we
different
draw a
color.
different color.
These
These
are
are
the
my
surface
surface
atoms.
atoms. Right.
And
And
because
because
they are
on they are on
on
another
surface,
surface
the right
or
and
the
back
right and
surface,
back
that's why
surface, that's why I'm
I'm
writing
writing
in
in
dotted
dotted line.
line.
Right.
Right.
Now
Now
what I'm trying
what
to
I'm
do is
trying to do is
let's
let's
draw
draw
it
it
for
for
1
one
1 1,
one one,
right?
right?
So I'm
So
trying to
I'm
cut
trying to cut
this
this
surface
surface along this surface.
Okay.
Okay.
Yeah,
Yeah,
there
there
is
is
another
another
one
one
here,
here,
right?
right?
This
This
surface.
surface.
Yeah.
Yeah.
So
So now
this one
this one
will
will
pass through
pass through
this guy.
this gap.
Yeah.
Yeah. So
We'll
we'll
have
have
another atom
another
here.
atom here.
So
So
my
my
plane
plane
is
is
this
this
one.
one.
Okay.
Okay.
And
This is my plane. This is
this is
my
my
111 plane.
I'm
I'm
trying
trying
to
to
cut
cut
the
a
crystal
crystal
along this
along
plane.
this plane.
Now
Now,
if I
if I
draw
draw
this
this
plane
plane
here,
here, this will be a
close
close
pack
pack
plane,
plane,
right?
right?
So
So
at
at
top
top,
I
I
have
have
this
this
atom,
atom, the
the corner
corner
atom,
atom,
and
and
here
here
on
on
the
the
surface
surface,
I
I
have
have
green
green
atoms
atoms
because
because
they
they
are
are
face
face
center
center
atom.
atom.
And
And
again,
again, it
this
is
is my
my
another
another
face
face
center
center
atom.
atom, and
And
these
these
are
are
my
my
corner
corner atoms,
atoms,
right?
right?
And
And
for
and for
simplicity, I have
simplicity,
drawn
I
like
have
this,
drawn
but they
like this, but
actually
they
look like
actually
this.
look like this.
Okay.
Okay.
So
So
they are
they're
perfectly
perfectly
packed.
packed.
That's
That's
why
why
we
we
call it
called
as
as
a
a
close
close
pack.
pack.
They're
They're
pretty
pretty
close to
close
each
to
other.
each other.
That's
That's
why
why
we
we
call
call
it
it as
as
a
a
close
close
pack
pack.
planes.
So
Uh, No, I guess I got it pretty big. Right. So you draw it green first. Yeah. So this is my green atom. This is my red. These are my corner atoms. So if I try to join
the
the
centers,
centers,
it will look like
it will look
this,
like this.
right?
Right. So
This is my
this is
one
my
one.
111 plane.
Now if I
Now,
try to
if I
cut
try to cut along this direction, right?
So now
So now
let's take
let's take
the face
the
center.
face
This is my
center. This is
focus
my
atom.
focus atom.
Okay.
Okay.
Now the
Now the
coordination number
coordination number
in
in
FCC is
FCC
12.
is
Why?
12.
Because
Why?
let's say
Because
this is
let's
my
say this
atom.
is my atom.
So this
So
atom
this
will be.
atom will be,
So
so let's say
this is my
this
focus
is my
atom.
focus atom,
Right.
right?
Now
Now
this is my
this
top
is my
one.
top one.
This is my
This is
bottom
my
one.
bottom one.
The same
The
goes for
same goes for,
yeah.
yeah.
So it
So it will be
will be more
a little more
complex. Let's
complex.
not
Let's not
draw that
draw
because
that
it
because
will again
it will
take
again
a
take
lot of
a
time.
lot of time.
We only
We
have
only have 10
10
to
to 15 minutes
15
left.
minutes
So
left. So
let's continue
let's
that.
continue that.
So each
So
atom will
each
be
atom will be
coordinated by 12
coordinated by
atoms.
12
So the
atoms. So the
coordination number is
coordination number is
12.
12.
Right?
Right?
Now,
Now,
yeah.
yeah.
If I
If
assume
I
this
assume
atom
this
is my
atom is
focus
my
atom,
focus atom,
okay.
okay.
Now
Now
I have
I
lost
have
this
lost
bond,
this bond,
right?
right?
Because
Because
it is
it is
bonded with
bonded with
this,
like
right?
this, right?
So I
So
have
I
lost
have
this
lost
atom.
this atom.
That means,
That means,
you know what?
you
Let
know
me
what?
draw
Let me
this
draw
so
this
that
so that
people can
you people can
understand.
understand.
Okay.
Okay.
So let's say
So
this is
let's
my
say this is
focus
my
atom.
focus atom,
Is my
is
black
my
one.
black one,
So that is my
so that is my
green.
green one.
Now
Now
my top
my top
one
one
and my
and my
bottom one.
bottom one.
Okay.
Okay.
Let me erase
Let me
this.
erase this,
Yeah.
please. Yeah.
Now
Now
what should I
what
draw?
should I draw?
Yeah.
Should I, yeah,
I will draw
I
the
will
green
draw the
atoms,
green atoms,
which are
which are
the back
the back
surface,
surface,
the front
the front
surface,
surface,
right,
right? The
top one
top one
and the
and
bottom
the
one.
bottom one.
Okay.
Okay. Yeah.
So
So
let me
let me
change those
change
colors.
those colors.
Let
Let
me
me
write it
write it
as
as, this is my
top one,
top one, one,
bottom one,
bottom one, one.
the
The
front one
front
two,
one, two,
back one two.
back one, two.
So
So
this is my
this is
top
my
one,
top one,
bottom one,
bottom one,
front
front
and back.
and back.
So how many?
So how many?
This is
This
like,
is like,
yeah,
yeah,
should erase
should
this
erase this guy
because they
because
come in
they come in
different
different
times, right?
times,
So
right? So
again,
again,
this is for a
this is for
plane,
a plane,
right?
right?
And same
And
repeats
same
for
repeats
this side
for
also,
this side also,
right? So these
right?
are
So
the
these
four,
are the four,
these are
these
four,
are
eight.
four, eight.
Again,
Again,
four here.
four
So
here. The
coordination number will
coordination
be
number will
12.
be 12.
Now,
Now,
if this
if this
atom,
atom,
I
if
cut
I cut
along
along
this plane,
this plane,
if I cut
if I
along
cut
this
along
plane,
this plane,
this is my
this
one,
is my
one,
one,
one.
one, one,
Then how
then
many
how
atoms
many
are
atoms
lost?
are lost?
So that's the
So that's
question.
the question.
So this
So
atom
this
is
atom
lost,
is lost,
right?
right?
And
And also
this guy,
this guy,
this surface,
this surface,
and
and
this atom.
this atom.
So three
So
atoms are
three
lost.
atoms are lost.
And whatever
And
the
whatever the
lattice plane
lattice
on
plane
left
on
side,
left side,
the back
the
one
back one
will remain
will remain
untouched.
untouched.
That means
That means
one,
one,
two,
two,
three
three
are atoms
are
lost.
atoms lost.
So
So
atoms lost
atoms lost
will be
will
equals
be
to
equals to
three.
3.
So
So
one will be
111
equals
will
to,
be equals
I'm
to,
writing
I'm
this as
writing
a
this as a
constant. Let's
constant.
say
Let's
this
say
as a
this as a
constant C1.
constant C1,
Then that will be
then that will be
C1
C1
times
times
number of
number
atoms
of
lost
atoms lost will
will be
be
3
3
divided by
divided
what
by
is
what
area
is
of the
area
plane,
of the plane,
right?
right?
Now let
Now
me
let
write.
me write.
Let's say this
Let's
is
say
my
this is my
a
A
by
by A by root 2, that is A root 2, right? Root 2A. I can write it as root 2A.
and we know
And
the
we know
relation
the
root
relation
2a
root
will be
2A
equals
will
to
be equals to
4r,
4R,
right?
right?
And
And
this distance
this
will be
distance will
equals
be
to
equals to
2r,
2R,
right?
right?
Now we
Now
know the
we
angle
know
is
the
60
angle is 60
degrees.
degrees.
So
So
sine
sine
60 will be
60 will
equals
be
to,
equals to,
if you want to
if
know
you
the
want to know
height,
the height,
then
then
opposite side
opposite side
height
height
divided
divided
by
by
adjacent side,
adjacent side,
which
which
is
is
root
root
2a.
2A.
Sine
Sine
60
60
will
will
be
be
root 3 by
root 3 by 2
2 times
times
h
h
by
by
root 2a.
root 2A.
Root 2
2
gets
root 2 gets
cancelled. So
cancelled. So
root 3 by
root 3 by 2A
2a
will be my
height.
height.
Now,
Now,
what is my
what is
area
my
of the
area of the
triangle?
triangle?
111
111
plane
plane will
equals
be
to
equals to
half
half
times
times
base
base
times
times
height,
height,
which
which
will
will
be
be
equals to
equals to
half times
half
what is
times
my
what is
base.
my base.
Base will be
Base will
equals
be
to
equals to
4r.
4r.
4r
4r
times
times, now
height is
height is
root 3
root 3
by 2
by 2,
root
3 by
2a.
2 a.
Again,
Now again,
root
root
2a
2a
equals to
equals to
4r.
4r.
So a
So a
equals to
equals to
2 root
2
2
root 2
r.
r.
So
So
finally,
finally,
half
half
times
times
4
4
r
r
root 3
root
by
3 by root 2
into
into
2
2 root 2 r.
root
Root 2 gets
2 gets
cancelled.
cancelled. So
So
root 2
root 2,
it
it
will
will
be
be
equals
equals
to
to
4
4
root 3
root 3
or
4 root
r
3
square.
r square.
Now,
Now,
surface energy will
surface
be
energy will
equals
be
to
equals to
delta
delta
H
H
divided
divided
by
by
bond energy
bond
per
energy
unit
per
length
unit length
times
times the
coordination number
coordination number
times
times
the
the
Avogadro
Avogadro
number
number
into
into
3 by
3 by
4
4
root
root
3
3
r square.
r square.
Now this is the
Now this is
surface
the
energy
surface
for
energy for
111 plane.
111 plane.
Now
Now
surface energy
surface
for
energy for
110
110
plane.
plane.
Again,
Again,
so
so the, these are the
corner
corner
atoms
atoms
and face
and
center
face
ones.
center ones.
We are trying
We
to
are
cut
trying
this
to cut this plane right.
so
So
delta
delta H
delta
delta H upon
bond
bond and
bond
bond
energy
energy
times
times the
Avogadro number
Avogadro number
into
into the
coordination number
coordination number
12
12
times.
times.
So
So
bond
the
energy
bond
lost
energy
will be
lost will be,
so this
so
one
this
will
one will
lost
lost.
one
One
is
is
the
the
bond lost
bond lost.
one
1,
two
2,
and
and
three
3,
four
4.
four
4
divided by
divided by.
now
Now
the area
the
of the
area
plane
of the
will
plane
be equals
will
to
equals to,
this is my
this is
A,
my A,
this
this
is
is
my
my again
root 2A.
root 2A.
So
So
area
area
of
of
110
110
plane
plane
equals
will be
to
equals to
A
A
times
times
root 2A.
root 2A.
Root
So
2
root 2
A square.
A square.
Again,
Now again,
A
A
is equals
is
to
equals to root 2
2 root 2
2
R.
root 2 R.
So
So
root 2
root
into
2 into
8 R
8
square.
R square.
So
So
8 root
8 root 2
R square.
R square.
Right.
Right.
Now
Now
gamma
gamma
110
110
will be
will
equals
be
to
equals to
delta H
delta H
upon,
upon,
or I can
or I
write
can
it
write
as
it as
C1.
C1.
Yeah,
Yeah,
C1
C1.
C1
C1
times
times
4 upon
4 upon
8 root
8
2
root 2
R square.
R square.
Now
Now
the next
the
one is
next one is
100,
100.
right?
Right. So these are the corner atoms. This is the 1 0. So this is lost. This will be my 3. This will be my 4. 8. Oh, it's not 3 again. It's 5. The number of atoms lost is 5. Right? So for this one too, it is 5. So the area of the 1 0 0 plane is a square. A 2a equals to 4r. So a equals to 2 root 2r. So a square will be 8r. Then gamma of 1 0 0 equals to c1 cross 4 by 8r. So this is c1 by 2r. Now to the 2 0 0. So the free energy, the surface free energy will be delta H upon bond energy times coordination number into n naught times the number of bonds lost. So that will be equals to 4 for 2 0 0 divided by the area of 2 0 0. Right. So smart area will be a. So a square in eta. 4 ones, 4 fours. It is 1 by 2r. So that's all about atomic planes.